Newton's method is one of the most powerful and widely used algorithms in numerical optimization. Let's start with intuition. Suppose we want to find the root of a function, that is, find x where f of x equals 0. At any current point, xn, we draw the tangent line to the curve. The slope of this tangent line is f prime of xn. Using the definition of a slope, changing in y over changing in x, we set up the equation 0 minus f of xn divided by xn plus 1 minus xn equals f prime of xn. This gives us the next point xn plus 1. Rearranging the slope equation, we get xn plus 1 equals xn minus f of xn divided by f prime of xn. This is a famous Newton's method update equation. Starting from any initial point, we apply this formula iteratively, each time moving closer to the root. After the first update, we are at xn plus 1. We draw a new tangent line at this point and apply the same formula to get xn plus 2. Each iteration brings us closer to the root. Newton's method achieves a quadratic convergence, meaning the arrow in each step is roughly proportional to the square of the arrow in the previous step. In general, x becomes x minus f of x divided by f prime of x, repeating until convergence. The convergence criteria is typically when the update becomes relatively small. This is the essential idea of Newton's method for finding the root of f of x. Watching the iterations unfold visually, we can see the sequence xn, xn plus 1, xn plus 2 rapidly approaching the root. Now, let's connect the root finding to optimization. When we minimize a tensor differentiable function f of x, the necessary condition is that the first-order derivative f prime of x equals 0. This is exactly a root finding problem, so we can directly apply Newton's method, but instead of finding where f equals 0, we find where f prime equals 0. For optimization, Newton's method becomes x updates to x minus f prime of x divided by f double prime of x. Here, f prime is a first-order derivative, and f double prime is a second-order derivative. Let's apply this to a concrete example. Consider the non-convex function f of x equals x to the first minus 4x cubed minus 6x squared. Plotted over range -2 to 5, we can say it has a complex shape with multiple ups and downs, a non-convex landscape where multiple stationary points can exist. Taking the first-order derivative and setting it to 0, 4x cubed minus 12x squared minus 12x equals 0. This cubic equation has 3 solutions, meaning there are 3 points where the slope is flat. Not all of them are minimal. Let's identify which one is a true global minimum. Among the 3 stationary points, one is a local minimum, a value that looks like a minimum nearby, but isn't the lowest overall, and one is a global minimum, the true lowest point of the function. Newton's method will converge to different stationary points depending on where we start. This sensitivity to the starting point is a key challenger for non-convex optimization. For our function, the first-order derivative is f prime of x equals 4x cubed minus 12x squared minus 12x. And the second-order derivative is f double prime of x equals 12x squared minus 24x minus 12. With both derivatives in hand, we can implement the Newton's method. The update equation at each step is x minus f prime of x divided by f double prime of x. Starting at x0 equals 5, we compute f prime of 5 equals 140 and f double prime of 5 equals 168. The first Newton step gives us x equals 5 minus 140 divided by 168, which is approximately 4.167. We have already moved significantly toward the minimum in just one step. Here we visualize the starting point x0 equals 5. On the function curve, we are starting far to the right of the minimum. Newton's method will use a tangent line and the curvature information to efficiently navigate toward the global minimum. Watching the iterations from x0 equals 5, we can see Newton's method rapidly descending toward the global minimum. The convergence is achieved in very few iterations. Now, let's try a different starting point, x0 equals -2 on the left side of the plot. This is closer to the local minimum region. Newton's method doesn't know which minimum is global. It simply follows a local curvature. Starting from x0 equals -2, Newton's method finds a local minimum, not the global one. This is a critical limitation of Newton's method on nonconvex optimization. The solution you find depends entirely on where you start. In practice, strategies like multiply random restarts or global search methods are used to address this challenge. Now, let's consider a classical 2D benchmark, the Rosenbrock function. This function was introduced by Howard Rosenbrock in 1960 and is a standard benchmark in statistics, machine learning, and scientific computing. The contour plot of the Rosenbrock function reveals its distinctive planar shape. The function decreases slowly along this valley and steeply across it. This makes a gradient descent struggle. It keeps bouncing across the valley instead of following it. Newton's method, with its curvature information, is much better suited for this landscape. The optimal solution of the Rosenbrock function is at x1 equals 1 and x2 equals 1, where the function value is 0. This point sits at the bottom of the curved valley. The challenge is getting there efficiently. Many optimization algorithms struggle with the Rosenbrock function precisely because the valley is so narrow and curved. But how do we extend Newton's method to 2 dimensions? We start at the origin point at -1, 1, far from the optimal solution at 1, 1. In 1D, the update used f prime and f double prime. In 2D, this becomes the gradient vector and the Hessian matrix. The first-order partial derivatives of the Rosenbrock function are given here. For Newton's method, we need to set this gradient equal to 0, which is again a root-finding problem, but in 2 dimensions. The second-order derivatives form the Hessian matrix. The diagonal entries are the second-order partial derivative with respect to x1 and the second-order partial derivative with respect to x2. The off-diagonal is a cross-partial derivative. This Hessian matrix captures all the curvature information of the function at any point. To minimize f of x1, x2, we convert to a root-finding problem, find where the gradient vector equals 0. In 1D, Newton's method updates x using x minus f prime over f double prime. In multiplied dimensions, the scalar division by f double prime becomes a multiplication by the inverse of the Hessian matrix. The multivariate Newton's method update equation is a vector x1, x2 updates to itself minus h inverse times a gradient vector. Here, h is a 2 by 2 Hessian matrix evaluated at the current point. This update uses second-order curvature information in all directions, allowing Newton's method to navigate the planar-shaped Rosenbrock valley efficiently. Remarkably, starting from -1, 1, Newton's method reaches optimal solution at 1, 1 in just 2 iterations. The path on the contour plot shows an algorithm taking a large curvature-informed step down through the valley. Comparing two starting points side by side, starting from -1, 1, Newton's method converges in just 2 iterations, starting slightly further away at -1.2, 1. It takes 4 iterations, still remarkably fast. Both passes navigate the Rosenbrock valley efficiently thanks to the Hessian matrix, demonstrating that Newton's method is robust to nearby starting points and achieves very fast convergence near the optimum. Thanks for watching this video. See you next time.